audio working? Okay.
Do you want to sit on this?
Sure. Wait, you're doing the... Okay. Wait. Okay. Hey everyone, welcome to the 2221 revision seminar. Before we get started, can I just get all of you to scan the QR code?
Can you teach me how to use this real quick?
Oh yeah, just scroll.
Scroll.
If you want to change it, just double click.
Double click.
Yeah. Like between the...
Oh, cool. Okay.
Yeah.
How about colors?
You just click.
Preference.
Okay, so for this revision seminar, we're basically going to cover everything. So we will be covering linear ODEs, dynamical systems, which will be Alex's part, and then we'll be covering initial boundary problems and generalized Fourier series, which will be my part. So I'll pass it on to Alex.
Alright. So yeah, there's going to be a lot of stuff to cover, so it's going to be quite a marathon, honestly. But in case you guys maybe miss anything, or if there's an example you want to go back to, these slides will be published onto the website later, so you can download them and just cherry pick exactly what you need. So let's just get straight into it. So we'll start off with topic 1, which is linear ODEs. So first off, we have the humble first order linear ODE, which is in this form right here. Wait, is there like a pointer tool? Like a...
Yes. This one here.
Okay, that's great. So it's in this form right here, and the way we solve it is we first multiply both sides by the integrating factor e to the integral of a. Now this is highlighted because it's something you should remember. And then by the product rule, our ODE turns into this. And then just a bit of algebra will show that our solution is going to be this. So that's just a formula, but let's see how we can use it to solve a problem. So we have this ODE, and it's first order linear. We just have to get it into the desired form so that we can use our formula. So we're going to divide through by t to get here. And now our integrating factor is going to be e to the integral of the stuff that's adjacent to y. So it's going to be this stuff here, which is right there. And if you integrate that, that gives you t e to the t squared. So that's going to be what you multiply both sides by. So once you do that, this stuff here very nicely cancels out with this. And so you're left with this. And then if you integrate both sides, you get the solution, which is very nice and easy. Any questions about the integrating factor? All right, moving on. Differential operators. So given some continuous coefficients, so these coefficients are functions, the LDO of order m is this expression right here, where the d case is a shorthand for the kth derivative, and then d of 0 is just the identity map. So a sub m is called the leading coefficient, and implicitly we want a sub m to never be identically 0. Otherwise, the definition of an order wouldn't really make sense. And then just a technical note, L is a linear map from Cm to C. And Cm here just means the space of m times differentiable functions. More definitions because we need to lay down the groundwork. So linear ODE and its corresponding LDO, we call it singular if the leading coefficient vanishes for some x in the interval. So for example, this ODE is singular because on 0, 1 because x is obviously 0 at 0, but it's not singular on 1, 2. a ODE is homogeneous if the right-hand side is 0. So for example, this is homogeneous. And then the set of all homogeneous solutions is the vector space ker_L, which is the kernel of L. Then obviously an ODE is inhomogeneous if it's not homogeneous. So the right-hand side is just going to be some non-zero forcing function f. Now, another type of problem is an initial value problem. So that's just going to be your normal ODE, could be forced, could be unforced. And then coupled with some data, which is this, and then that's going to give you what's called an initial value problem. So for example, you could have this ODE with this initial condition, and then you can check that the solution is just e to the negative x. Couple of theorems here. If f is continuous and the ODE is non-singular, then the one variable IVP has a unique solution. That's pretty handy to know. And another theorem is that if the LDO is non-singular, then the dimension of the kernel is equal to m, which is its order. So what does this imply? It implies that if we can find a basis of the kernel, then the general solution to the homogeneous equation is just going to be their linear combination like that. And then also, if we can find a particular solution to an inhomogeneous equation like this, then the general solution is just going to be the sum of UH and the particular solution. More definitions. So linear independence is going to be linearly independent if they satisfy this condition. Okay, moving on to our Wronskian. So our Wronskian is just defined as this determinant right here. And do note that the order of the columns do matter, which is why this notation is really nice because it actually like specifies the order of your columns so that you keep them in the right order. Okay, so why is the Wronskian useful? It's useful because it can tell you if functions are linearly independent. So this theorem says that if the Wronskian of some functions is not 0, not identically 0, then the functions are linearly independent. Then you've got the contrapositive here as well. And of course, the converse in this case is actually not true. So this is a counterexample that you can check by yourself. Here's a quick example. So functions cos and sine are linearly independent on R because they're Wronskian. So here's cos, its derivative, and then sine, and its derivative is going to equal to 1, which is not identically 0. So therefore, by this theorem here, cos and sine are linearly independent. Now there's another theorem that's pretty similar, and the only difference here is that now we're assuming the functions are solutions of a non-singular linear homogeneous nth order ODE. Then the Wronskian being non-zero is equivalent to these functions being linearly independent. So the subtle difference is that these are actually solutions to the linear diff equation. Right, now getting into a bit of machinery. Reduction of order. It's basically a way to generate another linearly independent solution. So if U1's a solution to an ODE in this exact form, then a second independent solution is going to be this expression right here. Now, I'm abusing the notation in the integral a bit. This should probably have like a U1 squared of x. And then the integral here, P actually does depend on x, but it's just written this way to be a bit more compact. Okay, so here's an example of how to use reduction of order. So we're given this pretty hard to solve ODE, it looks like, and and we're given that u1 is x cos x is a solution, then we need to find the general solution. So we can see that p of x, which is the term next to u dash, this should actually have a dash next to it. So p is minus 2 on x, and so e to the integral of p is going to be x to the minus 2. And so if we use the reduction of order formula, wait, the mic's been off the whole time. We get this expression right here, and this integral is going to simplify to x sine x, which means that x sine x is our second solution. So because of that, x cos x and x sine x are a basis of the kernel, which means that the general solution is just going to be their linear combination. Moving on to LDOs with constant coefficients. If L is a LDO with constant coefficients, then it's going to be a polynomial of the derivative operator. And this polynomial has to be unique, and it's called the characteristic polynomial of L. So for example, if L is this, then the characteristic polynomial is just this, where we've literally just replaced all the d's with x's. Okay, so here's an algorithm on how to solve the homogeneous problem for a linear constant coefficient equation. So first you want to find the roots of the characteristic polynomial, including the multiplicity. Very important, guys, including multiplicity. Then if the root lambda, which is a real one, appears k times, then these are all going to be linearly independent solutions. And then if you have complex roots like this, k times, then all of these are also going to be linearly independent solutions. And you can actually derive this from here using Euler's identity, which should be a pretty nice exercise to do. And after you've done that, we will have exactly the order of the LDO number of solutions because of the fundamental theorem of algebra. So that means we've got a basis of the kernel, so the general solution is just going to be their linear combination. So let's have an example and see how this method works. So if the characteristic polynomial has an x squared, we know that 0 is the root of multiplicity 2. So we're going to have terms that's like c1 and then c2x. Now, minus 3 from this second bracket is going to be a root of multiplicity 2. So that's going to give us a c3 e to the minus 3x, and then c4 x e to the minus 3x. Remember to multiply by x for each multiplicity. Now, we're going to need to find the solutions of this. I'm pretty sure this quadratic's irreducible, so we're going to use the quadratic formula to get minus 1 plus minus b squared is 1, then minus 4ac is 8, 1, 2. So that's minus 1 plus or minus I root 7 or 1, 2. So our real part's negative a half, our imaginary part's root 7 on 2. So that's going to be this case here. We have non-real roots. So we're going to have 4 terms that look like this. Those are going to be e to the minus half x, so the real part in the e part, and then the trig terms have the imaginary part in them. So we've got c5 cos root 7 on 2x plus plus c6 sine root 7 on 2x. And then the same thing, but we have an x out in the front, and so on. So that's going to be the general solution to the homogeneous problem. Any questions how we find that? Right, moving on to judicious guessing. There's a lot of text here, but I'm not going to go through all of it. But what's most important first is that this is a method for solving inhomogeneous problems. So we just looked at how to solve the homogeneous version. Now we're going to look at how to solve the inhomogeneous version. So when solving these, we should always solve the homogeneous problem first, and then we're going to find a particular solution by making a good guess. And there's honestly no need to memorize these formulas, because the key idea is to just try something that's similar to the forcing function. And if it's necessary, you just keep multiplying by factors of x until you escape the kernel, basically. So every part of your guess should be not a homogeneous solution. Okay, so this is probably best illustrated with a bunch of examples. So we'll go through these just very briefly. So for the first example, you can see that the characteristic polynomial is lambda cubed minus 3 lambda squared. And you can factorize that like this, which means that, which means that a basis of the kernel is going to be 1x and e to 3x. Now our forcing term is a quadratic polynomial, so ideally we'd want to guess a quadratic polynomial. But we do notice that 1 and x are in the kernel, so we're going to have to multiply everything by x squared so that our quadratic leaves the kernel, basically. So our guess for the particular solution is going to be a polynomial that looks like this, and then multiplied by x squared, so that we're not in the kernel anymore. For example 2, we do a similar thing. We take a look at the characteristic polynomial first. So that's going to be lambda squared plus 4, which has roots plus minus 2i. So that means the basis of the kernel is going to be sine 2x and cos 2x. Now, our forcing term is a polynomial times a trig function. So ideally, we would want to guess a polynomial of the same degree. So that's going to be a linear polynomial ax plus b, and then a combination of our trig terms. And hopefully something like that should be able to be a good enough guess. I'm going to leave example 3 and I'm going to leave example 4 and move on, because this next one is quite important, which is the idea of superposition. So to solve this type of equation, once again, you want to identify the basis of the kernel, which is going to be 1 e to the 2x and x e to the 2x. And then you want to do the right-hand side by parts, basically. So for the x term, ideally you'd want to try a linear polynomial ax plus b. But since 1 is in the kernel, we need to multiply by x, just so that the terms in our guess are completely outside of the kernel. And similar thing for the e to the 2x. Ideally, once again, we'd want kind of to match this form, so we'd want to try constant times e to the 2x. But since e to the 2x and x e to the 2x are in the kernel, then we need to multiply by x squared to fully escape it. So altogether, our guess is going to be a superposition of these two cases. So that's going to be this right here, where we've multiplied enough x's respectively. Now, once we have this guess, all we have to do is sub this back into the original equation and then solve for our constants. It turns out that they're going to be this. And then finally, we obtain the general solution, which is going to be that. So this part's the particular solution, and this part's the homogeneous part, which is a combination of these. Moving on to the annihilator method, which is only for the higher version of this course. So the idea is basically to start with a forced ODE, and we just want to find an operator A of D which annihilates f of x, which means that when you apply it to f of x, you get 0. So for example, D3 annihilates x squared. That's because if you differentiate x squared 3 times, you get 0. So what we want to do is apply this to both sides of this ODE right here. And then a solution to this new ODE is going to be a particular solution to the original equation. So we'll see an example of how to do this. First of all, there are some common annihilators we should know. If f is a polynomial, then you just want to use the derivative map raised to 1 more than the degree of the polynomial. If f is exponential, then this will do the trick. And if f is just a simple trig function, then this will do the trick. Okay, so we'll go through this example together. Okay. So first of all, we can see that the forcing term is sine of x. And so if we look over here for our common annihilators, an annihilator that's going to annihilate sine of x is d squared plus I. So that means we can rewrite our differential equation as d squared plus I d squared I'm very convinced that this should be a prime here, because otherwise it would be kind of weird. So we'll just assume there's a prime missing. So that's d squared and then plus d, u equals 0. So all we've done is apply our annihilator for sine x to both sides. Now, the characteristic polynomial of this here has roots I minus I, I minus I, and then 0 and minus 1, which means that u has to be in the form c1 cos x plus c2 sin x. So that's from the imaginary solutions, and then plus c3, and then finally plus c4 e to the minus x. So any questions how we just got that? Okay, so what we can notice here right now is that this part over here is a combination of the functions in the kernel of our original LDO. So this part is actually going to be the homogeneous part of our solution, and this part here is the real particular part. So what we want to do now is take this part here and and sub it back into this equation, and then solve for C1 and C2, and hopefully get a nice answer. And you can kind of see here that this is actually going to be the particular solution that we would have just guessed using judicious guessing anyways. And as a matter of fact, you can actually use the annihilator method to prove that the judicious guessing stuff actually works. Right, so if we sub UP here back into the original equation, what we're going to get is UP double is going to be minus C1 cos x minus C2 sin x, and then plus UP prime, that's going to be minus C1 sin x, and then plus C2 cos x, all equal to sin x. And remember before that we mentioned that cos and sine are linearly independent. So because of that, we can just equate the coefficients of cos and sine of both sides to get some simultaneous equations for C1 and C2. So that's going to give us, if we look at the cos terms on the left-hand side, we've got minus C1 plus C2 equals 0. And then equating the sine terms, we've got minus C2 minus C1 equals 1. So as you can see, the solution here is obviously C1 equals C2 equals 1/2. So that means the particular solution is going to be one half cos x plus 1/2 sin x. That's how you can find solutions using the annihilator method. So honestly, it's not really that much quicker than judicious guessing if you know what the guess is going to be, because you end up plugging the same thing back in anyways. But just so you know, this is how to do it because it might come up in an exam. Moving on to variation of parameters. So sometimes this is really useful because sometimes the forced term here is not going to be really nice, as with the judicious guessing. So it might not be a polynomial or exponential or trig function. So this is going to be a way, if you know how to solve the homogeneous problem, then we can construct a particular solution just from knowing a basis of the homogeneous problem. And that particular solution is going to be given by this formula right here. And yes, it's very important not to mix up U1 and U2, especially when doing the Wronskian. So highly recommend to just label everything as you go. Okay, so let's see how we can use variation parameters to do a past exam question. So first of all, as always with a forced equation, we want to solve the homogeneous problem first. So the characteristic polynomial is going to be this, which is just reading off the coefficients. That factors as that. So the basis of the kernel, we're going to take U1 to be e to the x, and U2 to be e to the 2x. And if we slap that into the Wronskian, we're going to get this. And now, using our variation of parameters formula, a particular solution is going to be given by this expression here. So U2 is e to the 2x, U1f is going to be this, our Wronskian is e to the 3x, and then sub everything in as per normal. This integral looks like we're going to need to use integration by parts to do, and then we'll get this here. Then eventually everything will simplify nicely into this. Now all we have to do is put everything back together. So this was the particular solution we found with variation of parameters. And then this here was the original homogeneous part, which is just a combination of the kernel. And note that for this one, we could have done a judicious guess. So the forcing term was e to the x sine x, which means that the guess would have been, I believe, e to the x and then a cos x plus b sine x. But this is going to be a nightmare to differentiate. So in this case, maybe if you're okay with integration by parts, then this is actually a much quicker method to solve the forced equation. Any questions about how we solve using variation of params? Yeah? Was that a hand? Alright. Okay, so yeah, once again, you can use whichever way you like, judicious guessing or variation of parameters, but variation of parameters is just going to be more reliable most of the time, so yeah. Moving on to using power series. So the idea is sometimes the equation is just too hard to solve analytically. Well, I guess like an elementary way. So what we want to do instead is just be happy with a power series representation of the solution. So here's the setup. We have an ODE with analytic coefficients. So that just means that the coefficient functions can be expanded as a power series. And we also need L to be non-singular on a neighborhood of 0. Now, we seek a power series solution of this form here. So this power series is going to be centered at 0, so it's pretty important that we're not singular at 0. So what we do is we basically just plug this guess into the ODE and rewrite the LU into some power series form. But that's going to be equal to 0 because we're solving the homogeneous problem. So that's going to force each of these coefficients to be 0. And then from here, you can obtain a recurrence for AK, and the number of degrees of freedom are going to match the order of L. And then lastly, you can check the radius of convergence using a ratio test. So that's a lot of description, but it's a lot simpler than it sounds, so let's just get into an example. So these are pretty useful to remember, just so that you don't have to rederive them every single time you do a power series problem. So this is just how you differentiate the power series. And then what I'm doing here is just re-indexing. So that's also very good to know. So if you shift the index down, you want to move everything up. That's basically it. And same thing here. What we've really just done is taken this series here, differentiate it term by term here, and then once again re-index it. So we want to shift k down twice, which means that every k inside the sum moves up by 2. So as you can see, k turns into k plus 2, k minus 1 into k plus 1, so on. Okay, so here's a past exam question. We have an ODE and we want to solve it using power series method because this doesn't look very easy to solve using our normal methods. And then finally, after finding the recurrence, we want to solve this IVP that they've given us. Okay, so let's go through this together. So first of all, we want to seek a solution in this form, right? So what I'm going to do first is rewrite our equation as the following. So we have got 0 equals u double plus z squared u double, and then minus zu prime minus 3u. So expanding that out term by term is just going to help me rewrite it as a bunch of sigmas. So this u double, if we use this power series form, we can just use this formula right here to get the sum from k equals 0 to infinity of k plus 2, k plus 1, a k plus 2, and then z to the k. I believe. Yeah. Now for this next term, since we have a z squared here, we actually don't need to re-index, because the goal is just to make sure that we've got z to the k's in all of these sums, and then we're going to bring it all together. So this time we're not going to re-index because we're going to be compensated by this z squared. So we're going to start at 2, and we've got k, k minus 1, ak, and then z to the k. So normally that would actually be z to the k minus 2, but because of this z squared over here, it's going to compensate, and this is going to become just k. Okay, a similar compensation's happening for the next term, so that's just going to be the sum from k equals 1 to infinity of k, ak, and then z to the k. And then finally, u, as we know it, is just going to be this. Any questions on how I just got that line over there? Okay, continue going in the solution. So now what's really nice is that we've kind of one-stepped it and gotten zk's everywhere. So what we want to do is make it into one big sum so that we can start equating things to 0. We do notice, however, that this sum starts at 0, this sum starts at 1, this sum starts at 2, so we can't do that straight away. So what we're going to do is collect outside the z to the 0 and z to the 1 terms, then write everything as a sum starting at index 2. So how that's going to work is the z0 term over here in this first sum is 2a2. This second sum doesn't have any. This third sum doesn't have a z0 term, but this last sum does, and that's going to be minus 3a0. Now we want to take out any z1 terms. So for the first sum, it's going to be 6a3. The second sum doesn't have a z to the 1 term because it starts at index 2. For the third sum, it's going to be minus a1. And for the fourth sum, it's going to be minus 3a1. So that's all with the z. Now that we've taken the z to the 0 and z to the 1 terms out, we can just rewrite the rest of this as a big sum starting at index 2. So that's going to be basically putting everything here together. So from the first one, we've got this expression. From the second sum, we've got this, and yeah, so on. We just continue collecting everything together into one big sum. Okay, so now since the left-hand side here is 0, and we essentially now have a power series of our guess, what needs to happen is that each of the coefficients must then equal to 0. So that means in our first one, we we must have A2 to be equal to 3 on 2A0. That comes from here. From this coefficient, that needs to be equal to 0. So that means that A3 needs to be equal to 4 on 6A1. And then for the rest, we need AK plus 2 to be equal to, if this is all 0, then just a bit of mental algebra, this is going to give you k squared minus 2k minus 3 all on that, AK, for k bigger or equal to 2. And can you simplify this? Yeah, actually you can. It's going to be k minus 3 on k plus 2, AK. For k bigger than or equal to 2. Actually, we can also just re-index this. So we want to bring k up to k bigger or equal to 4. So all the k's inside are going to shift down by 2. So that's AK is going to equal to k minus 5 on k, AK minus 2 for k bigger or equal to 4. Okay, so what we've done here is essentially we've obtained the relevant recurrence relationship for our coefficients. And we've also found out what A2 and A3 are in terms of A0 and A1. Now, A0 and A1 here are free. They're our degrees of freedom, which we mentioned earlier. And it makes sense that we have 2 degrees of freedom, A0 and A1, because remember, this was a second order equation. So there are 2 degrees of freedom. Okay, so this is our recurrence that the question wants. Now we need to find the solution to the IVP. So we're given that u of 0 is 0 and u prime of 0 is 6. So this just means that A0 is 0 and A1 is 6. So what does that mean? I'm going to change the color here just so that we know we're working on the next part. That means A2 is 0. And then from our recurrence here, since we're going in steps by 2, this recurrence is going to imply that A4 and A6 and so on are all going to be equal to 0. So all the even terms in our power series are going to vanish. Now, because of our initial condition that A1 is 6, we're going to have A3 to be 4. And if we put this into our recurrence, what's A5 going to be? Well, A5 is going to be 5 minus 5 on 5, A3. But 5 minus 5 is 0, right? So A5 is 0. And once again, because the recurrence is going in steps of 2, that also implies that A7, A9, and so on are all going to be 0. Okay, so if we collect together what we've got, the only non-zero terms that we have are going to be A1, which is 6, and A3, which is 4. So that means the solution to the IVP is going to be A1z plus A3z cubed, because all the other coefficients have vanished. So that's 6z plus 4z cubed. That should be the final answer. Okay. Any questions on this particular example? Alright, so as you can see, these types of questions are really just long. You just want to make sure that your algebra is done correctly and carefully enough so that you don't make mistakes. And hopefully once you've actually gotten the recurrence, it should be pretty straightforward. And yeah, nearing the end of this first topic. We have the Euler-Cauchy equation. So what it is just an ODE in this particular form, and A is not 0. Now note that it is singular at x equals 0, and a nice property that it satisfies is that if we apply our LDO here to XR, we get back a multiple of XR. So you might notice this, that XR is an eigenvector of our linear map. Well, actually we do call it an eigenfunction because it's technically a function. And then this is the eigenvalue. So that's a pretty important property of this particular map. So therefore, x to the r has to be a solution to the homogeneous equation if and only if this coefficient equals to 0, and this is called the indicial equation. So to solve the Euler-Cauchy ODE, we want to first find the roots of the indicial equation, which we'll call R1 and R2, and then we have three different cases. So if both the roots are real and distinct, then that's our answer. If the roots are equal, then that's our answer. And then finally, if the roots come in complex conjugate pairs, then this big expression is our answer. Now, you need to remember these because I'm pretty sure they won't be provided on the formula sheet in the exam. But it's really nice that you don't really have to remember the third one because you can derive it from the first one using Euler's identity. Right, so make sure these ones are drilled into your mind. Okay, we have an example here. So find the general solution of this particular forced Euler-Cauchy equation. So as with any forced equation, we want to first start off by finding the homogeneous solution. So the homogeneous problem is indeed Euler-Cauchy, and this is the indicial equation. And if we factorize it, we get this. And so the roots are going to be -3/2 and -1. And therefore, x to the -3/2 and x to the -1 are linearly independent solutions to our homogeneous problem. And that's just using the case 1 of the 3 different Euler-Cauchy cases. Okay, now we can use variation parameters to find a particular solution and then conclude our general solution. Or in this case, there's actually a very clever trick that we can use. So recall that if L is an Euler-Cauchy LDO, then the function x to the r is an eigenfunction of L, and its eigenvalue is the indicial polynomial. So why is this useful? Well, this is useful because our forcing term here is actually of the form x to the r, which means that our forcing function is an eigenfunction of this linear operator. So, since we know that linear operators map eigenvectors to a scalar multiple of themselves, a very natural guess, because the right-hand side is an eigenfunction, would be to guess a scalar multiple of it. So that's exactly what we're going to do. Notice that the forcing term is an eigenfunction, and so since we have an x to the 1/4, we're going to guess a constant multiple of it, which is going to be ax to the 1/4. And if we plug that in, we get this relationship here. And notice that all we've done here is substitute 1/4 into our indicial polynomial. So a was 2, b was 7, and c was 3 in our original question. And then if you cancel out these x to the 1/4 and then divide this over, we are ending up with a equals this number right here. So that's a really fast way to find the particular solution just with that very clever trick. And so the general solution is going to be this, where this is our homogeneous part and this is our particular solution we just got. So this is going to work for forced Euler-Cauchy problems where the right-hand side is a polynomial. And if you've got multiple different polynomial terms, you just got to superimpose them, just like we did in one of the previous examples. However, it's not going to work if you have something like an exponential or a trig function on the right side. It has to be polynomial because we're kind of leveraging that eigenfunction trick. So if the right-hand side's not a polynomial, then you're going to have to use variation of parameters. And honestly, it could get messy, so I don't really see that appearing in an exam, to be honest. Right, any questions on this particular example? Alright, so the last bit of this topic is obviously Frobenius, and okay, let's get to the definition straight away. So a lot of ODEs can be written in this particular form, which is the Frobenius normal form, and P and Q are analytic at 0, which means that they have power series, or I guess they're nice functions. Alright, they're nice. And to solve this, we seek a solution in the form of this kind of augmented power series. So this part's a power series, but then you're multiplying by this z to the r factor. And r here is a root of this polynomial. So this looks just like the indicial polynomial of the Euler-Cauchy equation. And that's because when we're very close to 0, this equation kind of behaves like an Euler-Cauchy equation. So for our purposes, we're only going to work with the case where the roots of this indicial polynomial don't differ by an integer, so that we can actually get linearly independent solutions. And here's how we do it. So just like how we did it in the power series example, all we do is sub this expression here, u of z, back into our equation, and then find a recurrence for our coefficients a, k. And then we've got two cases here. If our roots of the indicial polynomial are real, then each case is going to give a linearly independent solution. And if they're not real, then they're just going to be these. And once again, this does come from Euler's identity as well. So if you want, you can just remember this one and derive the second one on the spot anytime you want. And that's going to be it for topic 1. Moving on to dynamical systems. So the idea here is that instead of having one variable now, we have multiple variables, and we're just going to represent that as a state vector like this. So x is a vector, and then its components are x1 through to xn, and they depend on our independent time variable here. Bit of terminology. There are two types of systems. There is an autonomous system, which is if you can write it as dx dt equals f of x, and f doesn't depend on t. And then there's a non-autonomous version, which is if f explicitly depends on t. And then I'm not going to go through this, but essentially we don't care about non-autonomous systems because they can always be reduced to autonomous systems if we just package the t with the x into a one-dimension higher vector. Alright, so getting into a bit of pure maths here, we've got Lipschitz continuity, and this is the definition. this is definitely something that is important to remember, so make sure you've got this definition memorized. And how is nice to think about it is if you divide x minus y on both sides, then the left side is going to become the slope of a secant of a graph, right? So essentially what that means is that when f is differentiable, then Lipschitz continuity is just equivalent to having a bounded derivative, because once you divide this over, then what you've done essentially is bounded the slope by this constant L. So a quick way to tell if a function, if a real valued function is Lipschitz, is just to think of the graph. So if the graph has a bounded slope, so the slope doesn't become vertical, it should be Lipschitz. A couple of theorems here. If a function is Lipschitz, then it's uniformly continuous, so that just means it's a stronger notion of continuity. And then if a function is C1 on a compact interval, then it is Lipschitz. I'm pretty sure this theorem here is just a more formal way of saying this here, that if it's got a bounded derivative, then it should be Lipschitz. Yeah, because the derivative being a continuous function, it's going to be bounded on a compact interval by the min-max theorem. So yeah, it's saying the same thing as this. Okay, so here's an example. Is f of x equal e to the x Lipschitz on R? So immediate from intuition, the answer should be no. That's because if you think about it, on all of R, the graph of e to the x, it looks like this. And as you can see, as x goes to infinity, so as we keep going right on this graph, the slope becomes pretty much vertical. So the derivative's not bounded, right? So we should expect that it's not Lipschitz. But how do we prove it from definition? So what we're going to do is, for the sake of contradiction, just suppose that it is Lipschitz, which means that from the definition, we're going to have a constant L such that for every y, we have this inequality. But clearly this inequality can't be true because this ratio here approaches infinity as y goes to infinity. Which means that given any L, we can always find a y such that this value exceeds L, so that this inequality cannot be true. So that's a contradiction. Any questions about the way this is proved? Moving on, we can extend the definition to vector fields. I really doubt this kind of thing is going to get assessed, but we're just going to see that the definition is pretty much the same as in the one-dimensional case. And we're also going to define just being Lipschitz in one variable. So here, Lipschitz in x just means that you've got the Lipschitz condition for all x like this. So this stuff depends on time, but there's no time dependence here. And the reason why we want to extend those definitions is to provide a theorem that tells us when a dynamical system has a unique solution. So that's this local existence and uniqueness theorem here. And whilst it's not stated very rigorously, the key idea is just being locally Lipschitz is sufficient for a unique local solution. So essentially, if the function's nice, if it's elementary, in fact, there's going to be a unique solution, at least locally. And because solutions to IVPs are unique, an immediate consequence is that if you trace out trajectories in the phase portrait, then two different solutions can't intersect. So either they intersect completely or they never intersect. Right, moving on to the core component of this topic, which is going to be linear ODEs, linear systems of ODEs. So we say that this type of system of ODEs is linear if the right-hand side is of the form some matrix times our state vector and then plus some forcing vector. So the special case that we focus on mostly is when the matrix function is just a constant matrix. And so our system is going to reduce to this. And the general solution, assuming, this is very important, that assuming that A has n linearly independent eigenvectors, in other words, it's diagonalizable, then the general solution is going to be this right here. This linear combination of these eigenvectors. So that means solving a system where A is diagonalizable just amounts to finding all the eigenpairs of A, which is a linear algebra problem now. Now we're looking at the matrix exponential. So it's defined as this power series. We're not going to worry about convergence. This will always converge, actually. And then, yeah, what we can do instead is that if we've got this system here, then we can simply write the solution as e to the ta and then its initial condition. And this kind of parallels the one-dimensional case where you've got like u prime equals u, so that u is e to the x. So it kind of looks similar to this. So a couple ways to calculate it. If your matrix is nilpotent, then the power series of e to the a will truncate and it will be finite. So you can just compute that manually. If A is diagonalizable, we're going to look at that very soon on how to calculate e to the a. And then finally, if A can be written as the sum of two commuting matrices B and C, then we get this identity here. And this is nice just in case that e to the B and e to the C are easier to find than e to the A. Okay, let's go diagonalizing a matrix. So recall from linear algebra that an n by n matrix is diagonalizable if you can write it in this form, basically. So this is going to be a diagonal. Yeah. And then yes, a matrix is diagonalizable if and only if it has a complete set of eigenvectors. So you can find a basis consisting of eigenvectors of A, and then this relationship will hold where you chuck the eigenvectors into a matrix Q and then the corresponding eigenvalues into this matrix delta, pretty important that these are all in the same order. That way it's going to work out. And usually, I think it's more useful to write this relationship as A equals Q lambda Q inverse, because we want to compute powers of A, not lambda. So yeah, this is going to be the more useful way to write this. Okay, matrix powers. So yep, if A is diagonalizable, then the powers are pretty easy to compute, because when you multiply it, these terms here are going to cancel out and give you the identity, and then all you're left with is a bunch of cancellations, and then you've just got Q and then lambda to the K and Q inverse at the very end. And finally, if A can be diagonalized, then its matrix exponential is also easy to compute. It's just going to be Q and then e to the lambda and then Q inverse. And when you exponentiate a diagonal matrix, all you do is raise the entries to the power of e. And yeah, same thing here, you've just got the scalar t as well, and same thing applies. Okay, so now we know how to find e to the a for diagonalizable matrices, but not all matrices are diagonalizable. Some are defective, which means that you won't find a basis of eigenvectors. So in that case, we have a very handy method, which is Putz's algorithm, which will allow us to compute e to the a t when a is any matrix really. It can be diagonalizable, it can be defective, but we're going to use it mostly for the defective case. So that's the formula. A bit hard to read honestly, but here it should be a bit more clear. So if we define P of t to be this, and it satisfies this system of equations. So you've got the eigenvalues on the diagonal, you've got ones immediately below it, and then zeros elsewhere. That's an easy way to remember it. And then the initial data is just 1 followed by a bunch of zeros. Then, for the two-dimensional case, that is the formula for e to the at. And for the three-dimensional case, you've just got the two-dimensional case here, and then plus an extra term there. So these two should definitely be things to remember. And it'll be good enough if you just remember this, no need to remember the general case, because only the n equals 2 and 3 cases will be assessed. Okay, so I'm going to do a worked example. We've got this matrix here, pretty simple matrix, and we're going to do it in two ways. So the first way, we're going to compute it with Putz's algorithm, just to showcase how it works, how to set your working out. And then we'll find a different way to compute it, just to check that if we got the right answer. All right, so first I'll write down the formula. So e to the ta is equal to p1 of ti plus p2 of t, and then a minus lambda 1i, where lambda 1 is one of the eigenvalues. Now, since a is upper triangular, the eigenvalues are going to be the diagonal entries. So we're going to have lambda 1 equals lambda 2 equals 2 here, because that's the diagonal entries. And if you've taken linear algebra, you can see straight away that this is not a diagonalizable matrix because the only eigenvalue is 2, but the algebraic multiplicity is 2, so they're not adding up, basically. The geometric and algebraic multiplicities are different, so it's not diagonalizable, which is why Putz's algorithm is going to be really nice here. And what are the p's? Well, the p's satisfy the following system. So we've got p1 prime and p2 prime equal to, we've got eigenvalues down the diagonal, 1's below it and 0's elsewhere, and then p1, p2. And our initial data is going to be p1 of 0 is 1 and p2 of 0 is 0. So before we want to find e to the ta, we need to find out who p1 and p2 are first. So if we read off our matrix representation here, we are going to get p1 prime equals to 2p1, and keeping our initial condition in mind, that's just going to give us p1 of t to equal e to the 2t. Similar thing for the next one, we just take the dot product of this row with this column. So that's going to give us p2 prime equals p1 plus 2p2 this time. And this is a first order linear equation. So this is going to rearrange as p2 prime minus 2p2 equals, well, p1 is e to the 2t. Our integration factor is going to be e to the integral of whatever's hugging the p2 term. So e to the integral of minus 2, which is e to the minus 2t. So we can multiply both sides by the integrating factor, and that's going to give us e to the minus 2t, then p2 equals 1. And now integrating both sides, we have this. It is plus c, but our initial conditions will imply that c is 0. And so p2 of t is t e to the 2t. So now that we've solved p1 and p2, we can finally come back to finding our matrix exponential. So Putz's algorithm gives us this e to the ta. We only want e to the a, so we want to sub in t equals 1 first. So e to the a is going to be p1 of 1i plus p2 of 1. Now lambda 1's 2, remember, and a minus 2i is just going to be this matrix. So if we put that all together, we see that p1 of 1 is e squared, so e squared I, and p2 of 1 is also e squared, so that's plus e squared in this matrix. And if we simplify this, this is our answer using Putz's algorithm. Okay, now we're going to use a second way to find this, which is a bit more efficient. What we can realize is that A is equal to 2i plus n, where n is this matrix here. So n in this case is nilpotent, and because it's a 2 by 2, that means that n squared is 0, which you can check. Now, because 2i and n commute, that means that e to the a is going to be equal to e to the 2i times e to the n. important fact is that e to the ki is always going to be equal to e to the k times I. So this is going to become e squared I. And now because n is nilpotent, our power series is going to truncate. So e to the n, we can expand the power series out for the matrix exponential, which is I plus n, and then you've got n squared on 2 factorial plus the other terms. But since n squared is 0, and any further powers of n is going to be 0, these are all going to cancel out. So we're just left with I plus n. So that's going to be e squared times I plus n. But I plus n is just the matrix 1, 3, 0, 1. So overall, we do get the exact same answer in a fraction of the time. So this is a nice way to check if your Putz's matrix is correct, because sometimes in the exam, they will specify to only use Putz's algorithm. So if you have any extra time left, once you've got this answer, maybe try a different method like this, see if you get the same thing, just to check if you're right. Moving on to the fundamental matrix. So these are the properties it satisfies. So what's important is that the columns of your fundamental matrix are actually linearly independent solutions to your system. So that's, if you're going to remember one thing, that's what you should remember. That the columns of the fundamental matrix are linearly independent solutions. Now here are some properties. So every solution to this is just the fundamental matrix times some constant vector. And yeah, if you've taken multivariable calculus, this is a pretty nice exercise to try and prove. Then the next very important property is that if phi is any fundamental matrix, then e to the ta equals this product of matrices. This is highlighted because it's very important. You should definitely know this. Right, so here's an example on how to restore the fundamental matrix. And this is kind of like working backwards. So if you know the general solution to a linear system, then you can just restore it. So for example, let's say this is the solution to some linear system. So by that I mean x prime equals ax, where A is a 2 by 2 matrix. Then we can express it like this, so just collecting these vectors together into one vector, and then splitting up into a matrix and a constant vector. And then we just read this off as the fundamental matrix. And that's how you do it. That's how you retrieve the fundamental matrix if you know the solutions to your equation. Alright, now it's going to be the first real application of these matrix exponentials. You can see there's a lot in this formula. So the variation of constants formula is how to solve the forced system of linear equations. So yeah, that's the one you've got to remember right there. f is 0, then you've got the homogeneous problem again. So this whole integral vanishes, and then you're just left with e to the TAC, which of course is the general solution to the homogeneous problem. Right. So let's look at an example of a variation of constants problem. Okay, looks like we'll go through this one together. So we are given that this is the general solution to this linear system, and here A is a constant matrix, and we want to solve this problem. Pretty standard exam style question, honestly. So first of all, if we want to use the variation of constants formula, we need to know what e to the TA is. And the easiest way to find that out is by reconstructing our fundamental matrix. So if we read off our solution here, a fundamental matrix is going to be e to the 2t 0, and then t e to the 2t, and then e to the 2t. So that's our fundamental matrix. Now we want to know its inverse as well. So the formula for the inverse is this. So if we have a matrix A, B, C, D, then its inverse is going to be AD minus BC, then DA minus C minus B. So if we use that here, we have e to the 4t on the bottom, and then the other entries are going to be e to the 2t, e to the 2t still, then minus t, e to the 2t over there. And so therefore, e to the TA, which is what we're going to need soon, is equal to this, and then the inverse evaluated at 0. But it looks like the inverse evaluated at 0 is just the identity matrix. So this goes away, and then this is 1, 1. The determinant's also 1. So it looks like very nicely here, e to the TA turns out to be the fundamental matrix. Now this is not always going to happen, it's just a very nice coincidence in this case. Okay, so by the variation of constants formula, the solution to this IVP is going to be x of t equals e to the TA, and take the integral of e to the minus SA, and our forcing term, which is this over here. So e to the 2s and 6s e to the 2s ds. Then finally plus e to the TA, and then our initial data. So x0 is 0, 1. So it's going to be that. Now, what is e to the minus SA? E to the minus SA is going to be e to the minus 2s, and then minus s e to the minus 2s. So basically just replacing all the t's from our fundamental matrix with minus s's. So this is going to simplify to e to the TA inside this integral. Do e to the 2s times the first column, so that's 1 in the top and 0 in the bottom. And 6s e to the 2s times the second column. That's going to give us minus 6s squared in the top, and then 6s in the bottom. And this term here is just going to be the second column of e to the ta. So that's just this here. Okay, now integrating this term by term, we get e to the ta t minus 2t cubed. And then the integral of 6s, that's going to be 3t squared. Then all we have to do now is just evaluate this matrix vector product, put everything together, and that's going to be the final answer. Moving on now to equilibrium points. So a point A is an equilibrium point of a dynamical system if f of A is equal to 0. So that means that if you've got dx dt equals f of x, then f of A is a constant solution to the dynamical system. Now, the equilibrium point is stable if all of this is satisfied, but intuitively, all that means is that if you've got a trajectory that starts close to A, then it will stay close to A as t moves forward. And then asymptotic stability is a stronger form. So this is the formal definition, but intuitively all we care about is that if you've got a trajectory that starts sufficiently near A, then it will approach A as t goes to infinity. So for example, a stable equilibrium might look something like this. So here's your equilibrium point, and if your trajectory starts somewhere here, it might just stay within this circle as t moves on. But if you've got an asymptotically stable point, then if you've got an equilibrium here, a trajectory that starts close to it is going to approach it. So that's the difference. Okay, so if we've got this linear system as we've studied before, then it has a unique equilibrium point given that A is invertible, that's what this means, and that is going to be given by this vector. Now, if A is diagonalizable, right, this is very important that it's diagonalizable, then if these are the eigenvalues of A, then the equilibrium point is stable if and only if the real part of all these eigenvalues is smaller or equal to 0. And then it's asymptotically stable if and only if the real parts are all strictly smaller than 0. And if the real part of any eigenvalue is positive, then the equilibrium point is unstable. As we've seen before, if we have linearly independent eigenvectors, then this is going to be the general solution to this system right here. And then if they're complex conjugates, then all we have to do is extract the real and imaginary parts and then take a combination of that. Okay, so we're going to look at all the different types of equilibriums. So the first one is a stable node. So what this happens is when your two eigenvalues are smaller than 0 and they're not equal. And it's going to look something like this. Any trajectory is going to be closing into 0, like that. Now the unstable one is just the complete opposite, which means that any solution is going to move away from 0, basically. So as you can see in this phase portrait, you can see these arrows pointing away from 0. Now a star is if you've got two equal eigenvalues. So that will actually mean that A is a scalar multiple of the identity, which is why when you start somewhere, you're just going to move out in an array like that. So your star will attract inwards if lambda is negative, and it's going to go outwards if lambda is positive. Then the last real case is a saddle node. So that's when one eigenvalue is negative, one's positive. And what's going to end up happening is it's going to look like hyperbolas like this. So here are your eigendirections in the picture. And then you've got hyperbolas like this. And the flow of the solutions is going to start near biased in the direction of the negative eigendirection, and as time moves forward, it's going to bias towards the positive one. Okay, now looking at what the cases of imaginary eigenvalues. So if they're purely imaginary, then your solution terms are going to be pure sine cosine. So as you'd expect, solutions are just going to rotate around. So as you can see, this is exactly what happens. You can see these kind of ellipses being formed. And now if it's got a real part and an imaginary part, then what you'll end up with is a spiral. So if the real part's negative, then it's going to be attracted into the center. And if the real part's positive, then the spiral is going to go away from the center. Okay, any question about all those different cases? It's a lot. Okay, we'll quickly look at an example of solving a system and then classifying the equilibrium point. So how do we solve this? First of all, we're going to rewrite it as a matrix like this. So we're just reading off the coefficients and chucking them into a matrix. And now the eigenvalues of this matrix, this is a neat trick to compute them quickly, is that they sum to the trace, which is the sum of diagonal, and their product is the determinant. So now that you've got a sum of roots and a product of roots, you can make a quadratic equation and then retrieve the eigenvalues. They're going to be 3 and -4. So now we need to find the corresponding eigenvectors. So for the first one, lambda 1 equals 3, we need to find a vector in the kernel of A minus 3i, which is the eigenspace of lambda 1. So that's going to look like this. And therefore, this is an eigenvector corresponding to lambda 1. And in a similar way, if we try and find a vector in the kernel of A plus 4i, then we'll find that an eigenvector for lambda 2 is 1, 1. Okay, so now that we've got our eigenvalue and eigenvector pairs, we can just write down the general solution by combining. So we've got a constant, we've got e to the eigenvalue t, and then the corresponding eigenvector, another constant, e to the eigenvalue t, corresponding eigenvector. And now what's the stability of the center? Well, because one of the eigenvalues was negative and one was positive, the equilibrium point is going to be an unstable saddle node. And the phase portrait is going to look like this. So here's our xy plane. Here's the 1, 1 direction, roughly like this. Here's the -6, 1 direction, roughly like that. So those are going to be the axes of our hyperbola, which means that some solution curves are going to look like this. Now the direction of the flow is going to be biased towards this one, because this one kind of diminishes as time goes to infinity, but this one is dominant. So our arrows are going to go this way because this is the -6, 1 direction. So arrows go this way, and this way. Now another important point is that if a solution starts on these axes, then it's going to stay on these axes. So for the -6, 1, they're going to get repelled away from 0, so arrows go in these directions. But if it starts on the 1, 1 axis, then because this approaches 0 as time moves forward, the arrows are actually going to go inwards like this. And that's the complete diagram. Any questions on how that diagram was made, or anything else about equilibriums? Cool. Okay, so now we're going to look at the last part of this topic, which is nonlinear systems. And we'll just study a couple of ways to basically analyze the stability of equilibrium points. So the first one is local linearization. And what it says is that if you've got an equilibrium point A for a nonlinear system, then at least locally you can determine its stability by studying the Jacobian matrix evaluated at A. So this is going to make more sense if I just do an example. So we're going to determine the stability of the fixed point 0, 0 for this system here. So this is essentially x prime equals f of x. This is the first component of f, and this is the second component of f. So that means the Jacobian of f is, well, it's going to be the first entry is the first component differentiated with respect to x. So that's 1 plus 2y. And the second component is the first component differentiated with respect to y. So that's 1 plus 2x this time. Now we do the same for the next component on the next row. So this with respect to x is -2, and the same second component with respect to y is 1 plus 3y squared. So there we go, that's the Jacobian of f. Now what local linearization says is that we just need to study the Jacobian matrix of the fixed point. So if we plug in our fixed point 0, 0 here, we get the matrix 1, minus 2, 1, and 1. Now the eigenvalues of this matrix are going to determine locally the stability of 0, 0. So the characteristic polynomial is the determinant of 1 minus t, 1 minus 2, and then 1 minus t. That's 1 minus t squared plus 2, which is t squared minus 2t plus 3. And to find the eigenvalues, we want to set this to 0, so that's going to be, yeah, actually we could have just done it right here. So if that's 0, then t minus 1 is plus or minus I root 2. So t equals 1 plus or minus I root 2. So the thing about here is that you've got complex eigenvalues and the real part is positive. So since the real part of the eigenvalue is positive, we know that this has to be unstable. And because we have a complex thing, it's going to be a spiral. So locally, it's an unstable spiral. Moving on to the next method of analyzing stability for nonlinear systems is Lyapunov's method. So the idea here is to find an auxiliary function v that is the first two say that it's positive definite, so it's always positive except at 0, where it evaluates to 0. And then the third one is just a regularity condition, which basically means that it's always going to be decreasing. So if you can find a function that satisfies all of these, then the fixed point 0 is stable. And then if you can find a function v such that 3 is a strict inequality, then the fixed point 0 is asymptotically stable. So let's have a look at how to use this to analyze the stability of a point. So we've got this system here. Once again, this is basically x prime equals f of x, where this is our first component of f and this is our second component of f. So we want to try and satisfy the third condition first. This is going to be the most easiest to work with. First of all, since we want v to be positive, I'm actually going to just straight out of the bat take m to be 2, because if we do this, then part of our answer is already positive anyways. So ideally, we're going to find the n for the y to be an even number, so that their sum is always positive. Okay, so what we want is for the gradient of v dotted with f to be smaller or equal to 0. So what is this expression here. So if we see here, the gradient of v is just the vector where the first component is the thing differentiated with respect to x. So since we chose m equals 2 straight away, this is just going to be 2ax. And then the second component is the thing differentiated with respect to y. So that's going to be b n y n to the minus 1. Now we just dot product that with this over here. So that's going to give us 2ax minus x minus y squared x, and then plus this second component of f right there. So we want to choose a, b, and n smartly enough so that this can simplify down. So this is minus 2ax squared, then minus 2a x squared y squared, and here we've got a minus b and y to the n terms, and then more x squared terms. Okay. So we seek constants a, b, and n so that this is smaller or equal to 0 at all inputs. So what I can see here is that we've got an x squared term here, an x squared term there, that is coupled with a y. So what I'm going to do is I'm going to choose y to be, choose n to equal 2, just so that I can put those two terms together. And then I'm going to choose a to be 1 and also b to be 1. And then this is just going to give me minus 2x squared minus 4x squared y squared and minus 2y squared. And because this is a negative sum of squares, this is certainly smaller or equal to 0. In fact, it's strictly smaller than 0 for all non-zero x and y. So what do we have now? We have found that our function of interest is going to be v of xy equals 2. Subbing these values back into our hint here, we've got x squared plus y squared. Now this is absolutely positive definite, and we've got this condition here satisfied. So that means by Lyapunov's method, 0 is asymptotically stable. Any questions on Lyapunov's method? Okay, sweet. Okay. Final part of this topic is limit cycles. So quick definition, a cycle is a non-constant periodic solution to x prime equals f of x. So what does that mean? It means that a cycle, when you draw it in the phase portrait, it's going to look like a loop. It's going to be a closed trajectory. So something like this, where it just keeps traveling into itself on and on in forward time. So if this cycle acts as the limit of nearby solutions, then it's called a limit cycle. And we classify limit cycles as stable if nearby solutions are attracted to it, and unstable if nearby solutions are repelled by it in forward time. There's also one called semi-stable, because if you think about it, a loop, it's got two sides, right? It's got the inside and the outside. So sometimes you might have a situation where things are going to get attracted to it from the inside, like this. So maybe that's the trajectory in forward time for one solution. But maybe on the outside of the loop, then trajectories might be repelled by it in forward time. So on one side it's attracting, on the other side it's repelling, and that's kind of called semi-stable. It's just an extra thing. Okay, so here's an example. This one is an example using polar coordinates. So a bit of a harder example, honestly. So we've got this non-linear system, a bit of a monster of a system here, and the question asks us to determine all the limit cycles and classify their stability. Okay, so let's do this worked example together. So first of all, this looks pretty hard to work with if we stick with x and y, because we've just got polynomials inside of trig functions and stuff. So what we want to do is, as this says here, convert it into polar coordinates. So as we see, we've got the x squared plus y squared. That's just r squared, which is really nice. So it seems like that's the right thing to do. So if we start off with r squared equals x squared y squared, implicitly differentiating that with respect to time is going to give us r prime r is equal to x prime x plus y prime y. And now we can just substitute these equations into here. So that's going to be x prime is x prime x is going to be x squared 1 minus cos pi r squared, then minus xy. So that's the x prime x bit. And the y prime y bit is going to be a very similar thing. We've got a y squared 1 minus cos pi r squared, and then plus xy. So fortunately here, these cross terms cancel out, and so we're left with x squared plus y squared, and then this common factor. So if we put everything together, this is going to simplify really nicely down to r prime equals r, and then 1 minus cos pi r squared. So that's our equation for r. Now for theta, we can start with the polar relationship tan theta equals y on x, right? And if we implicitly differentiate both sides, we're going to get theta prime sec squared theta equals, so just use the quotient rule here, so that's top prime bottom minus top bottom prime, and then x squared on the bottom. Now what I want to do is bring this x squared over to the other side, because I know that x squared times secant squared theta is equal to r squared, and that's just because of the polar relationship between x, r, and theta, because x is r cos theta, which means that x sec theta is equal to r. So if I times x squared on both sides, we're going to get theta prime times r squared is equal to, so y prime x, that's going to be this stuff. Looks like we have plus x squared as well. And then minus yx prime. It's going to be that. So another fortunate cancellation. These cancel, and then we're left with x squared plus y squared, which we know is r squared. And everything cancels out perfectly, and we have theta prime equals 1. So this is our second equation. So now we've got this system here. It's kind of decoupled actually. We've got this r prime equals this function of r, and then we've got theta prime equals 1, and that is equivalent to our original system. So now we want to find the limit cycles. First, notice that because theta prime equals 1, so that means like the angular momentum of your trajectory is constant. If you start at some r away, at some radius r away, your solution is just going to keep spinning around like this, right? That's what this here tells you. Now, what's really important is this equation here. Because this is going to tell you exactly where the limit cycles are. So that's going to happen when r prime is equal to 0. So when r prime is equal to 0, we either have r equals 0, which is just the equilibrium point at the center of the xy plane, or we've got cos pi r squared equal to 1. So that means that pi r squared is 2n of multiple pi, which means that r is equal to the square root of 2n, where n is 1, 2, 3, and so on. So actually we have a countably infinite number of cycles. Now, to explain why these are limit cycles, we can observe that this expression for the derivative of the radius is never negative. So it's always increasing because cos is between -1 and 1. So this difference here is always non-negative. And r is of course non-negative. So the whole thing is non-negative. So what that means is that if your solution starts at a radius that is not on one of these cycles, in forward time, what's going to happen is the radius will continue to increase. And of course, because solution trajectories can't cross over, they're going to be attracted to the next limit cycle. So that's why they're actually limit cycles, because they attract nearby solutions. So if we draw a picture, it's going to look something like this. So here's the xy plane. Say this is our first cycle, which is root 2. Our radius of root 2. Here's our next cycle, which is a radius of 4. Our next cycle has a radius of root 6. If we start on one of these cycles, what's going to happen is we're just going to keep spinning in this direction forever. So that's not very interesting. But what is interesting is that if we don't start on a cycle, then r prime is positive. So as time increases, what's going to happen is, let's say your trajectory starts here. You're going to spin clockwise because you're going to spin anti-clockwise because of this here. And because your radius increases, your trajectory is going to look something like this. And it can't cross the limit cycle because that's a different solution, right? So it can't cross, which means that it gets attracted to that cycle there. Same thing if something starts over here. The radius is going to increase as time increases, and it's going to get attracted to this cycle. So all of these cycles are limit cycles. Now they're stable on one side because they're attracting the inside solutions, but the solutions on the outside are getting repelled from it and they're getting attracted to the next limit cycle. So these ones are actually interestingly, semi-stable. So stable on one side, unstable on the other side. Okay, that was a lot for that example. Are there any questions about that?
Shouldn't the 4 just be a 2, just in case it's
The 4 should be a 2?
Is it root 4?
Yeah, that's right.
I don't know if you're keeping the diagrams.
That's right, yeah. It should be a root 4, so that should be a 2, sorry. Yeah, thanks for spotting that. Yeah, so, yeah, that's just some very nice qualitative analysis. So from converting from Cartesian into polar, you can see here that we can do all this and deduce all these limit cycles. In fact, there are countably infinite many in this case, and they all have this semi-stable behavior. Okay. Now the final part of this topic is Bendix-Dulac theorem, which in contrast, we just found the limit cycles. Now we're gonna do the opposite, which is prove that they don't exist. And so here's the statement of this theorem. So F is a vector field and alpha is a scalar field, and they're both C1 on a simply connected region. Simply connected just means that the region essentially has no holes. And if you've heard of Green's theorem, that's actually used to prove this theorem. So that's why we need it to be simply connected, because Green's theorem, part of the assumptions is that you're integrating over a simply connected domain. So if the divergence of this vector field scalar field product is of one sign on the region, then your system of equations x prime equals f of x has no limit cycles contained in D. If you've done a multivariable calculus course, or maybe an engineering course, this is an identity you might know. So this is pretty useful for computing this gradient very quickly, this divergence very quickly. And sometimes it might be useful to just note that because this quantity, well, it's a function, right? The divergence function. This is a continuous function. And so checking that this is never equal to 0 on D is also sufficient to show that it's of one sign because of the intermediate value theorem, right? If it's never 0, then that means because of continuity, it never crosses, so it's of one sign. Any questions about the statement of this? Okay. I'm sure you guys know how to use this theorem because it was in the previous class test. But we do have a harder example, so let's go through that. So this time, this notation here means the quadrant 1. So if this is the xy plane, then the domain of interest is this quadrant 1 here. And yes, that's simply connected because there's no holes. Okay, so we have this non-linear system and we want to show that it has no limit cycles. So we do have a hint here to make it a bit easier to find the sufficient Dulac function. But we're going to do the computations first and then maybe try and use the hint if we need it. So how to set this out? We'll start by saying if alpha equals alpha of xy, then the divergence of alpha times f, and implicitly here f is just the vector valued function whose first component is this here and the second component is this here. So if we use the identity we had before, that's going to be the gradient of alpha dot product with f, and then plus the divergence of f multiplied by alpha. Okay, so we need the divergence of f first. So the divergence of f is going to be the first component differentiated with respect to x. So that's 2 minus 2x minus y, and then plus the second component differentiated with respect to y. So that's plus 4 minus 2x minus 2y. And that's going to simplify to 6 minus 4x minus 3y. Okay, so now plugging our stuff into here, we're going to have the partial of a with respect to x, then dot product with the first component first, so that's going to be x 2 minus x minus y. And then you've got the partial with respect to y, and then the next component, so that's going to be this. And then finally, the divergence of f, which we've already found, times alpha. Okay, so the reason here why this is a nice guess for the Dulac function is because when you differentiate it, like with respect to x, this x is going to compensate for the power lost. And similarly here, when you differentiate this with respect to y, this y here is going to compensate for that power lost from the yn, right? It's going to become n y to the n minus 1, but this y is just going to bring it back to n to the yn, right? And we have this alpha here conveniently. So if we do take or guess that alpha is in this form, then what we're going to find is that this turns into m x to the m y to the n 2 minus x minus y. Then for this next one, we have got n x to the m y to the n, and 4 minus 2x minus y, and then 6 minus 4x minus 3y, x to the m y minus y to the n. So what's nice here is that now we've got these common factors of x to the m and y to the n that we can take out. So let's do that, and hopefully things can simplify a bit. So that's going to be, on the next slide, x to the m, y to the n, 2m minus mx minus my plus, then distributing this n in, we're going to have this. We've got this expression here. I think we can probably try and factor it a bit as well, just to help us get an idea of what to choose for our m and n's. So we've got 2m plus 4m plus 6. So that's these terms out of the way. Now we want to put the x's together, which is going to be minus x m plus 2n plus 4, and then put the y's together finally. So that's m plus n plus 3. Okay, so remember our goal was to make sure that this entire expression is of one sign for all x and y in the first quadrant. So we want to choose m and n so that that actually happens. Remember that when you choose your m's and n's, or any undetermined coefficients, you want to make sure that the expression continues to become simpler and simpler. So what we're going to do here, an idea is, we have this stuff here, we have this stuff here. It would be really nice if we can get rid of these negative stuff, right? We've got the minus x, we've got the minus y. Those might mess up our one sign kind of result we're going for. So what we're going to do is essentially equate these to 0 so that we've got these simultaneous equations. So we've got m plus 2n to be minus 4, and then m plus n to be minus 3. And that's going to be our choice for m and n, basically. So if we solve this, subtract 2 from 1, we're going to get n equals minus 1, which means m is minus 2. So let's take this to be our m and n. So that means this becomes 0 now, that becomes 0, so that's gone. If we sub n equals minus 1 and m equals minus 2 into here, this is going to become minus 4 minus 2. So altogether, we've got minus 2 x on x squared y. And is this all of one sign on the first quadrant? And yeah, it is, because this stuff's always positive in the first quadrant, and this stuff is negative. So this is a valid dual-arc function. So therefore, with the choice alpha of xy to be xm yn, so that's 1 on x squared y. There are no limit cycles. That's this example done. Any questions about that last example there? Alright, hope you enjoyed the first 2 topics. I'm going to hand it to Yui now, who will do topics 3 and 4 to finish. Thank you.
Okay, before we continue, can I just get those who joined us to just scan the QR code? So now we're going to start with the third topic. So starting off with inner products and norms, we say that the inner product of a continuous function is basically just the integral bounded from a to b of the product between the functions f of x and g of x. And just like, I guess, the dot product you have learned in high school, you say that 2 functions are orthogonal if their inner product is equal to 0. And now moving on to the norm, we say that the norm of f defined on the interval ab is just equal to the square root of the inner product of f with itself. And if you, I guess, just sub in your g to be your f, you can just kind of rearrange the equation to get the square root of integral from a to b of f of x all squared. So I think that's pretty intuitive. Now we're going to move on to some examples. So if we want to find the inner product between f and g, we can say that the inner product of fg is equal to the integral from 0 to pi of sine x cos x dx, which is just equal to half of 0 to pi sine 2x dx, which is equal to half of minus cos if you rearrange this equation, you should get that this is equal to 0. Yeah. Okay. And now if you want to find the norm of f, you can say that this is just basically equal to the square root from 0 to pi of sine squared x dx, right? And once again, just using our double angle formula, you can rearrange this into half of 0 to pi of 1 minus cos 2x dx. So if you evaluate this, this becomes half of x on 2 minus sine 2x on 2, bounded from 0 to pi. Sine of anything to a multiple of pi would just be 0. So you're just left with, I accidentally put the half out. Okay, yeah, it should be that. You can just sub in the pi into the x on 2, and that should become square root of pi on 2. Okay, so that's done. Pretty straightforward example. Okay, so that's just kind of the written up examples. Okay, now moving on to inner product of inequalities. So yeah, pretty straightforward. Just like the inner product you have learned, just like the dot product you have learned in high school, the Cauchy-Squartz inequality and the triangle inequality also applies. So these two inequalities should be pretty familiar to you guys. And now moving on to our next example. So we are given these three integrals here, and we want to find the largest value of this integral here. So what do you recognize about this integral here would be that this is basically just the inner product of f plus g h, right? And you'll also recognize that this is basically just the norm of f squared, and that this is just the norm of g squared. And then here, this is just the norm of h squared, right? And from there on, you can just kind of use the inequalities you have seen from before. You can basically write this to be equal to f plus g h. And here you can just kind of consider absolute value to actually use our Cauchy-Squartz inequality, right? So you can say that this is less or equal to the norm of f plus g multiplied by the norm of h. And once again, you can just kind of use your triangle inequality to further kind of, I guess, simplify this. So you can say that this is lesser or equal to the norm of f plus the norm of g multiplied by the norm of h, right? And from here, you can just sub in the expressions. You know that the norm of f is just square root of 1, so that's just 1. And then the norm of g is just the square root of 4, which is equal to 2. And the norm of h is the square root of 9, so that is equal to 3. If you just sub everything in and simplify this expression, you should be able to get that this is equal to 9. So therefore, you can say that the largest possible value of this integral here is 9. Any questions? Okay, nope. I guess we'll move on to the next part. Yeah, this is once again the typed up solutions. Okay, so moving on to linear two-point BVPs. Basically, it's a problem of the form this year, and in general, we can kind of generalize this form into some, I guess, differential operator of u and write it in terms of f. And you can see here that I guess these kind of match up with these conditions here. A fun fact you can, I guess, see is that B1 and B2 here are actually known as our boundary operators. So yeah, just a little fun fact for you to know. Okay, and now moving on to a very important theorem. We say that if the homogeneous problem, so aka when f is equal to 0, alpha 1 is equal to 0, alpha 2 is equal to 0, has only the trivial solution u is equal to 0, then we say that for every choice of f alpha 1 and alpha 2, the inhomogeneous problem has a unique solution. And one thing I'd like to note here is that this actually applies for 2-point BVPs as an if and only if statement. So what that means is that the forward direction is true, but also the converse direction is also true. Okay, so now moving on to, I guess, another question. So our question is, does the following BVP have a unique solution? So what do? You kind of just first find the homogeneous solution first, right? So if you consider the polynomial, which is just r squared plus 1 is equal to 0, this implies that r is equal to plus minus I. And you'll recognize from part 1 that you can write UH of x to be C1 cos x plus C2 sine of x, right? Now you can just kind of sub in the boundary conditions. So u of 0 is equal to 0. You have that UH of 0 is equal to C1, which is equal to 0. And that UH of pi is equal to minus C1, which is also equal to 0. So from these two conditions, you can kind of imply that C1 is equal to 0. So therefore, UH of x is just equal to C2 sine x. However, you would know that this is not a trivial solution. So not a trivial solution. Right, so what that implies is that there is no unique solution. So yeah, this is basically just using the theorem you have seen from the previous slide. Any questions? Okay, no, I guess we'll move on to, once again, it's just typed up solutions. We'll move on to adjoint operators and Lagrange identity. So suppose you have some, I guess, differential operator this here. We can kind of define the formal adjoint. So you write L adjoint V by this sign here. And then from there on, you can also deduce what P of UV is. And you can just write it as this form here. And this theorem is very nice. The Lagrange identity kind of ties, I guess it kind of forms a relationship between L and its formal adjoint by expressing the inner product of LUV with the inner product of UL adjoint V plus P of UV bounded from A to B, right? So this identity is very, very neat because it ties them together. And you will see how it's useful in this example here. So I guess, first of all, we consider some differential operator and apply it to U and say that is equal to minus U dash dash, and that x is bounded from 0 to 1 with the boundary conditions U of 0 is equal to U of 1 is equal to 0. And then we want to kind of show that the eigenfunctions corresponding to distinct eigenvalues are orthogonal without solving the differential equation. So one way you could kind of go about this is to, I guess, first consider L of U is equal to lambda U and L of V is equal to lambda V, where lambda is not equal to mu. And the reason for that is because in the question it's given that they are distinct, right? And then you would also note that L is equal to L adjoint, which implies that it's self-adjoint. And you can quickly check yourself using this thing here, right? In this case, our A2 is equal to 1, sorry, not 1, minus 1. A1 is equal to 0, and our A0 is equal to 0. So if you just sub in this into the formula in the previous slide, you can prove that L is equal to L adjoint, right? And from here on, we can just kind of use our Lagrange identity. So we can say that the inner product of LUV is equal to ULV plus P of UV bounded from 0 to 1, right? Now here that the reason why I could remove the stars because once again L is equal to its adjoint. Okay, so now you kind of want to simplify this expression and hope that is equal to 0, which in this case it should. If you evaluate P of UV, this should be equal to U dash minus V minus U minus V dash. And this is just once again using this formula up here, so pretty straightforward. If you simplify this, you should be able to get that this is equal to minus U dash V plus U V dash, right? And then what's left is you just sub in the bounds from 0 to 1. So note here that because we wrote that LV is equal to mu V, we also know that this condition here holds for V as well. So you can kind of say that V of 0 is equal to V of 1 is equal to 0. So if you sub in the bounds from 0 to 1 into this here, you should be able to get 0, right? So you can say P of UV bounded from 0 to 1 is equal to 0. Okay, so that's kind of the hard part done. Because you know that this thing is equal to 0, you can now say that the inner product LUV is equal to the inner product of ULV. And from here on you can just kind of, I guess, factor out the eigenvalues, right? Because you have previously set one of them to be lambda, one of them to be mu. So you can kind of just say that lambda UV is equal to mu UV. And if you write this all into one side, this implies that a bit out of space, but UV should be equal to 0. And what does this mean? It means that U and V are orthogonal to each other. So therefore we have proven that the eigenfunctions are orthogonal to each other despite them having distinct eigenvalues. Any questions?
Lambda and mu different, distinct.
Yeah, they should be different. Yeah.
I think you just write at the top that they're equal.
Because like lambda and mu, they both satisfy this equation here, you can also write lambda V to be, I guess, some scalar multiple of V. So it follows the same operation, but then it's not the same thing.
You need to write lambda equals mu at the top.
Wait, sorry, can you repeat that?
Did you mean to write lambda equals mu at just at the top?
Oh wait, sorry, yeah, that should be not equal to.
Oh,
Yeah, my bad.
Oh.
Okay, and that's just kind of the typed up solutions. Okay, so this is kind of like an adjoint operator example. So we want to find the formal adjoint of this thing here. So if we say that this is equal to A2, this is equal to A1, and this is equal to A0, you can once again just sub it into the formula from before. So you can say that L adjoint V is equal to A2V double dash minus A1V dash plus A0V. Yeah, you kind of just sub in the terms. So this becomes XV dash dash minus minus sign of X V dash plus E to the X plus 1 V. This is just kind of a bunch of tedious algebra. I think I'll just leave it up to you guys to do it yourself because it's pretty straightforward. But if you want the final answer, this should be what it simplifies to. So you can, I guess, give it a go yourself and check your answer. Okay, so now moving on to formally self-adjoint operators. I think I've kind of talked about this before. We say that an operator self-adjoint is if L is equal to L adjoint, right? So pretty self-explanatory. And now we kind of just have this theorem here which states that a second order linear differential operator, L is formally self-adjoint if and only if it can be written in this form here for some value P and Q, right? And from here on you can can also kind of have a go at this example for yourself if you want. But generally for questions like this, you want to kind of consider the integrating factor. So in order to do that, you want to make the leading coefficient to be equal to, I guess, 1. So if you divide both sides by x squared, you have u dash dash plus u dash on x minus 2u on x dash, x squared is equal to f on x squared. And then if you just consider the integrating factor, so mu of x is equal to e to the 1 on x dx, which is equal to e to the ln x, which in this case is just equal to x. And yeah, in this case, the sign of it really doesn't matter. So you were wondering, yeah, it doesn't really matter. So now you can just kind of times both sides by x and kind of try to write the first thing in terms of a diff of something, right? So you can say that x u dash or dash minus 2u on x is equal to f on x. Again, this is just timesing both sides by x. And then because you want to like kind of match this negative sign, you can times both sides by minus 1. So this becomes minus xu dash dash plus 2u on x is equal to minus f on x. And I guess if you want to make it nicer, you can also state what your p and q values are, but I won't do that here. I think you guys can check for that yourself. I think, yeah, down here in the solution, I've written the values for p, q, and g in this case. In this case, I set g to be the differential operator of u, so that's where that g came from. Any questions? Nope. Okay, so now to the Fredholm alternative. So once again, it's kind of like similar ideas. If we consider like this system here, we say, I think I've said this before, but if the homogeneous system has only the trivial solution, then the inhomogeneous system has the unique solution for every choice of f alpha 1, alpha 2, which I think we did that example before already, right? And as I've said before, it works for if and only if. So the converse also works in this case. But the other case is the homogeneous system has a solution if and only if this thing is true for every solution phi to the homogeneous system. So in this case, u plus cp is also a solution for any constant c, right? And now we, of course, have another, I guess, example. So under what conditions does this have a solution? So this here you can just kind of check yourself, right? I just realized I think that should be u. Let me just fix that. Yep, so if you consider r squared plus 1 is equal to 0, you have r is equal to plus minus I. And if you just sub things in, you should be able to get that solution. Okay, and then now we have to kind of consider R1v and our R2v. So R1v is equal to minus p of 0 a cos of 0 over 1, which is equal to minus 1 a on 1, which is equal to a. And then our R2v is just equal to p of pi a cos of pi over 1, which is equal to minus 1 times a plus minus 1 over 1, which is equal to a. Now here, how did I get this p? Again, I just kind of rearranged it into the form. So for this here, you can just rearrange it into minus u dash plus u, right? And from there on, you can just kind of consider your p-value to be equal to minus 1 and just sum everything in. Okay, so continuing on, now you can just kind of consider the inner product of f(v), which is equal to alpha 1 r 1v plus alpha 2 r 2v, which implies that the inner product FV is equal to A multiplied by the integral from 0 to pi of f of x sine, let me just fix that, f of x sine x dx, which is just equal to A alpha 1 plus A alpha 2, right? And then you can just kind of say that 0 to pi of f of x sine x dx is equal to alpha 1 plus alpha 2 after you just cancel the a's from both sides. But yeah, that's pretty straightforward. Just kind of subbing things into the formula again. And that is the written up solutions. Any questions? Okay, nope. And yeah, that's the other written solution as well. Okay, so now we will go on to generalized Fourier series. So just like our inner product from before, we can kind of also consider, I guess, an additional weight now. So if you, I guess, write the inner product with like a little w at the bottom, you can say that the inner product with the weight w is equal to this form here. We know here that the weight function is always greater than 0 on the interval a, b. And then once again, kind of like the norm from before, now you have the additional weight. So you can say that this is just equal to square root of the inner product between ff with the weight w. And same as before, you just have the additional w of x function here. Yeah, same thing. For orthogonality, except now you have the additional w, so we say that this whole thing is equal to 0 when it's orthogonal. And obviously orthogonality of sets also works the same. Okay, so kind of now for kind of the generalized Fourier series. So if we consider some series of functions, phi 1, phi 2, all the way to phi n, let it be some orthogonal sets in this. We say that if f is in the span of this set, then this is true. And our AK here is just equal to the weighted inner product over the normal phi k squared with respect to the weighted function. And this is just kind of a, I guess, additional interesting example. I don't think something like this will be tested, but I guess it's just interesting to, I guess, look at. So if we consider some phi n to be like a complete orthogonal set, and we want to show that P and F is the unique function such that it minimizes the norm of f minus g over g is an element of the span from phi 1 all the way to phi n. So the way you go about this proof is to obviously just consider the inner product between like f minus P and F and phi k, and you can obviously just sub this whole thing in, and from here on you can just kind of expand it out how you would normally would. Note here that everything disappears except for when n is equal to k, and this is basically just equal to the inner product between f and phi k, because a n once again is just this thing here. So if you sub that whole thing in, you would realize that this whole expression is just equal to 0. So what can you say about that? Since the two elements in the inner product are, when combined, are equal to 0, you can say that they are orthogonal to each other. Okay, so now we kind of suppose that V is an element of Vn. So it follows that this is an element of Vn, and it's also orthogonal to that. So then you can just kind of write your f minus g to be like f minus this term here plus this term minus g, because these two would just cancel out in the end. And because these two are orthogonal to each other, you can kind of just use your Pythagoras, right? So if you kind of like take the square root of the sum of the squares of the two, you get this here. And if you, I guess, subtract out this term, you will get that this is slightly smaller than this. And if you then take the square root of both sides, you should be able to get this inequality. So what does this it means that Pn of f actually minimizes the norm of f minus g. And now here the inequality only occurs when this whole thing is equal to 0, which is exactly when Pn of f is g. So therefore we know that Pnf is a unique solution. Any questions? Yeah, as I said before, this probably won't appear in the test, but I guess it's just interesting to look at. Okay, so now moving on to completeness. So basically we say that an orthogonal set S is called complete if no non-trivial solution is orthogonal to every function S. So i.e. this thing here. I guess in a way this can be thought of as a basis. And these are some examples you could try yourself. So I guess for these type of examples, you want to find some function f of x multiplied by, I guess, this function here, such that the integral bounded from minus pi to pi is equal 0. So maybe something like this. Let me just fix that. Right. And then you can just kind of, I guess, check for all three cases. From memory, I think these two were not complete. Only this one was complete. But yeah, have a go at that yourself. Okay, so now moving on to some norm theorems. So we have Bessel's inequality. So we can say that the Fourier coefficients in a generalized Fourier series of f satisfies this form here. And we also have Parsifal's identity, which states that if the set phi 1 all the way to whatever, it is, and let it be like some complete orthogonal set. If ak kind of like denotes the k coefficient, then we can say that this expression here holds. So this is just kind of another more interesting example of proving whether something is complete. So we're supposing that phi n is some complete orthonormal set, and we define like lambda n to be the sum of phi n plus phi n plus 1. So the question is this complete? So the first thing you can consider is, I guess, some function f. So consider f to be orthogonal to every lambda n. So then you have that the inner product between f and lambda n is equal to the inner product of f phi n plus phi n plus 1. And you can just kind of expand this out. So this becomes f phi n plus f phi n plus, let me fix that, not plus, phi, f of phi n plus 1, okay. And because it's orthogonal, you can say that this is equal to 0. So now you can just kind of let an to be equal to the inner product between f and phi n. So then we have that an plus 1 plus an is equal to 0, which implies that an plus 1 is equal to minus an. If you just sub in random values of n, you would quickly find a pattern such that an is just equal to minus 1 to the n minus 1 a1. Okay, so I'm gonna move on to the next page. Okay, so we can say that since phi n is orthogonal, well actually, I guess orthonormal, I guess we can use Bessel's identity, which gives that the sum of n is equal to 1 to infinity of the absolute value of the inner product between f and phi n squared is less or equal to the norm of f whole squared, which is less than infinity. So now we can say that since an is equal to minus 1 to the n minus 1 multiplied by a1, we have that the sum from n is equal to 1 of absolute value of an whole squared is equal to sum from n is equal to 1 to infinity of a1 so what can we say here? We can say that an is equal to 0 when this is like finite, right? So we can say that this is finite only if an is equal to 0, which implies that f phi n is equal to 0. And we also know that since phi n is complete, f is equal to 0, which implies that lambda n is also complete. Okay, so that's done. Any questions? No? Okay, I guess we'll move on. Once again, this is just the written up solutions. I guess we can move on to the next part now. Okay, so this is kind of just a Fourier series example. So this stuff is kind of just a bunch of rote learning. You kind of just, I guess, memorize the form and just sub things in. So in this case, you're given some orthogonal set, so 1 and some cos multiple of x, and we want to find the Fourier series representation of this thing here, where x is bounded from minus pi to pi. Okay, so here we kind of just use Parsifal's identity to evaluate the resulting infinite series as well. If you just sub everything into here, you should get this expression here. Note that norm of 1 squared is just equal to 1, 1. And you can just kind of put that into the integral, and you should be able to get 2 pi. So that's where this expression came from. So if you simplify everything, you should be able to get that this is equal to pi cubed on 12. Okay, and then now you kind of also consider the case for when n is greater or equal to 1. So if you consider the case for when n is greater or equal to 1, you also do the same thing, except now you kind of just have to use integration by parts. So after your integration by parts, you should be able to get this expression here. You can also equivalently write this as some piecewise function, where you consider when n is odd or even. And this is kind of just, I guess, an exercise left for you guys. You guys can just, I guess, try to find this yourself. You kind of just sub in all the parts we found from before and put it all together. Okay, so now moving on to Sturm-Liouville's equations. So we say that is an ODE of the form of this thing here, where P, Q, R are all real valued, where P of x is greater than 0, R of x is greater than 0, and x is bounded between A and B. And some eigenstuff. We say that a non-trivial solution phi to this ODE is said to be an eigenfunction with the eigenvalue lambda. Then phi lambda is referred to as an eigenpair. Okay, and now kind of moving on to our next example. Once again, for stuff like this, you kind of just consider the integrating factor. So if you divide both sides by 1 plus x, you would get this here. Right. And now we just consider integration factor, which is mu of x, which is e to the x plus 2, 1 plus x dx. So this becomes e to the 1 plus 1 plus x dx, which is equal to e to the x plus ln 1 plus x. Again, the sign here doesn't really matter, so you can just kind of cancel it out, because we know that x is between 0 and 1 anyway, right? So this becomes 1 plus x e to the x. Okay, so you kind of just times both sides by the integrating factor. So this becomes e to the x, x plus 1, u dash is equal to, actually minus lambda u e to the x is equal to 0. Because when you times this term by this here, the 1 plus x, they cancel out. So that should be your final form. And that's just kind of the written up solution of what we did before. so moving on to, I guess, the regular standard views eigenproblems. So usually the problem is given in this form here, where all of these coefficients are, I guess, finite reals with these conditions given here. And I think we've kind of talked about this before. Once again, when our eigenfunctions orthogonal, that is when the inner product is just equal 0. Except now, because your weights are, you want to times it by r of x inside the integral. And we also know that eigenvalues are real, so the eigenvalues from a regular standard view eigenproblem are real, right? Now we will analyze the completeness of eigenfunctions. We say that the regular standard view problem has basically an infinite sequence of eigenfunctions, phi1, phi2, all the way to whatever, that forms a complete orthogonal set on the interval AB with weight of r of x. So what we can say now is that the eigenvalues kind of satisfy this increasing chain where kind of lambda k approaches infinity as k approaches infinity. Okay, so one question would be, can this here be eigenfunctions of a regular standard view problem on 0, 1 with positive weight? The answer is no, because if you consider e to the m plus n x, this here is always greater than or equal to 0, right? Because x is between 0 and 1, and the weight is positive, so therefore, no, you can't. But ideally during an exam, you'll probably want to write the whole integral yourself. But like this is kind of the reason why. Okay, so now we want to consider the following ODE, this thing here. And on the interval 0, 1, what equality must any two of eigenfunctions for the above equation obey? So here, once again, you just kind of consider the integrating factor. So if you consider u dash dash plus 3u dash on 5 minus lambda u on 5 is equal to 0, mu of x is equal to e to the 3 on 5 dx, which is just equal to e to the 3 on 5x. And here you just kind of times both sides, so u dash e to the 3 on 5x dash minus lambda u on 5 e to the 3 on 5x is equal to 0. Because you have it in this form here, you can just kind of say that the integral from 0 to 1 of 1 on 5 u of x, phi of x, e to the 3 on 5x is, dx is equal to 0, just by that thing there. So yeah, pretty intuitive. And that's just kind of the written up solution. Okay, so now moving on to, I guess, another example. So we want to consider temperature u of xt in above length t, and u satisfies this expression here under position such that x is an element from 0 to L, and the times positive is positive. So the bar satisfies the following boundary conditions. And from here, we kind of just want to use the method of separation of variables and kind of let u to be xt. So usually for these types of questions, you will just write that u of xt is equal to xx t of t. But if you kind of want to like make your life a bit easier, you can just write it as u is equal to xt. And this here would just be like xt dash is equal to c squared x dash dash t, right? So for stuff like this, you kind of just want to, I guess, put everything into a fraction and kind of say that is equal to some scalar constant lambda. I think I have space here. So we can say that xt dash is equal to c squared x dash dash t. So therefore, t dash on t tc squared is equal to x dash dash on x, which is equal to lambda. And if you just kind of rearrange these expressions, you have that x dash dash minus lambda x is equal to 0. And you also have t dash minus lambda tc squared is equal to 0, which matches up with what they want here. And that's just kind of the typed up solution. Okay, so now we kind of want to find the boundary conditions. So once again, we know that u of xt is equal to x of x, t of t. So we have that x of 0, t of t is equal to 0. And we also have that x dash of L, t of t plus kappa x of L, t of t is equal to 0 from just kind of subbing stuff into this expression. So what can we say? We know that t of t can't be equal to 0, right? Because then it will be trivial. This becomes x of 0 is equal to 0. And the same thing goes on here. We know that t of t can't be equal to 0. So if we factor the t of t, we get that x dash of L plus kappa x of L is equal to 0. So these are just kind of the conditions that x must satisfy for you to solve the problem. And these are the written up solutions. Okay, so now we want to kind of consider the cases. So for when lambda is greater than 0, when lambda is equal to 0, and when lambda is less than 0. So for the first case, when lambda is greater than 0, we want to show that only the trivial solution exists. So suppose that lambda is greater than 0, then we can just consider some mu, which is some greater than 0, such that lambda is equal to mu squared. So I guess what we can see from here is that x dash dash minus mu squared x is equal to 0. And I guess from part 1, you can just kind of put it into this expression here. So how I got that was if you just consider r squared minus mu squared is equal to 0, you have that r plus mu. R minus mu is equal to 0, so therefore r is equal to plus minus mu. And because your r is equal to plus minus mu and they're real numbers, you can just kind of say that x of x is the sum of two exponential expressions with this as the power, or with this multiplied by x as the power. Okay, so that's pretty straightforward. Now you just kind of consider x of 0 is equal to 0, and you just sub everything in, right? So you have that c1 plus c2 is equal to 0, so therefore c1 is equal to minus c2. And we also have our other condition, which is this thing here. If you sub this all in, you should be able to get this here. And because you know that your c1 is equal to your minus c2, you can also sub this into this expression here, right? So after you sub everything in, you can kind of just rearrange. And you can just times both sides by e to the mu lambda. And because this expression here, the bottom is like very big and the top is like small, this has to be less than 1. However, we know that e to the x is greater than 0 because once again, our x is greater than 0, right? And because that kind of contradicts it, this implies that c1 is equal to 0 and also implies that c2 is equal to 0. So the only solution really is the trivial one. Okay, so now you consider when lambda is equal to 0. We want to show that in the case of when lambda is equal to 0, only the trivial solution exists for x. So if we suppose that lambda is equal to 0, very obviously your x dash dash is just equal to 0. So then you just have like x dash is equal to ax, and then your x is equal to ax plus b. So yeah, pretty straightforward. And then once again, it's just kind of subbing the boundary conditions. So when x is equal to 0, x of 0 is equal to 0. So from there on, you can just kind of find that b is equal to 0. And from our other condition, sub everything again, you get that a is equal to 0. And because x is just equal to ax plus b, you can kind of just say that x is also the trivial solution. Okay, now you kind of want to consider our last case, which is when lambda is less than 0. So we want to show that in the case of when lambda is less than 0, there exists some, I guess, non-trivial solution for x. So once again, you just kind of consider minus mu squared, x now is negative, so you take the negative of mu squared, and you just put it in. And once again, this is just considering the polynomial r squared plus 1 is equal to 0, which implies that r is equal to plus minus I. And using, I guess, the stuff you learned from part 1, you can just kind of write this as the sum of two trigonometric expressions. Okay, so once again, you can just kind of sum in the bounds. So when x is equal to 0, your x of 0 is equal to 0, we would find that C2 is just equal to 0. And then from our other condition, you can just kind of rearrange everything. So if you divide both sides by C1, and then kind of divide both sides by sine x, you should be able to get that tan of mu L is equal to minus mu NK. And if we kind of take our mu n to be the nth solution of this equation, we find that this expression here is true. So that is just kind of the non-trivial solution for x. Okay, now we want to find all possible solutions for Tn of t. We already know that this only exists when lambda is equal to minus mu squared, because the other two are trivial, right? So if you kind of just rearrange this expression here, this becomes like t dash is equal to minus c squared t. You recognize that this just simplifies to some exponential with obviously the constant at the front. And from our previous part, we know that this only really exists when lambda is equal to minus mu n squared, right? So you kind of just sub everything into this expression because our lambda is our minus mu n squared. And in order to find the general solution, you just put this whole term here into this sum here, and write that u of x of xt is just equal to this sum here. Again, pretty straightforward. Where in this case, our mu n is the nth solution of this thing here, as we have found in the previous part here. Okay, so that's just kind of how you would approach those problems. But this is kind of, I guess, a general approach to how you would approach those problems. This is a summary. So I guess generally, like your first step would just be to consider u to be equal to x of x and multiply by t of t. And then you would kind of determine the conditions of x and t. So you would kind of like sub in the values. Like, for example, we have done before, x of 0 is equal to 0. And kind of just sub everything in. Then you can either consider, this is what we did before, we considered the different cases of lambda. So when lambda is negative, when lambda is equal to 0, or when lambda is greater than 0. Or we can kind of solve the resulting ODEs using existing methods previously taught, I guess, in part 1. And then we use superposition to find the general solution. Okay, so now moving on to elliptic operators. So in general, we can kind of write a general partial differential operator in the form of this here. If we let A to be like some matrix formed from a second order coefficients, we can kind of have this elliptic definition, right? So we can say that the second order linear partial differential operator is called elliptic in omega if there exists some c greater than 0 such that this expression here is true. And this is just kind of a question you can do. So we are given some term alpha, and we want to consider the partial differential operator to be this thing here. And we want to determine all values of alpha for which L is elliptic. So I guess the first thing you can do is to, I guess, put this into a matrix. And now here you'd want to consider the negative of this term here. So consider 2uxx plus 3uyy plus uzz minus 2 alpha uxy. Right, so then your matrix would just be 2 minus 2 alpha 0, 0, 3, 0, 0, 0, 1. Let me fix that. Yeah, like so. And then you just want to kind of times the transpose. So, yep, that. Multiplied by this matrix, I'll call it A. Multiplied by this vector again. Right, and after you simplify everything, you should be able to get this expression here. So if we complete the square, done so here, you can see that this term is always positive and this term is also always positive. So the only term that could necessarily not be positive would be this term here. So from here on, you can just consider, I guess, when is this thing greater than 0, right? So in order for the whole thing to be greater than 0, you consider when this is greater than 0. So if you consider this inequality here, you can just rearrange everything and find that alpha squared is less than 6. And I guess you can like draw a little graph to then determine that alpha is between minus square root of 6 and square root of 6. And then kind of simplify the expression further by then saying the absolute value of alpha is less than square root of 6. So yeah, that's done. Now moving on to the divergence form. So note here that a little like the I is just denoted by this partial derivative here with respect to xi. So what is, I guess, the gradient of some random function u? We say that the gradient is just equal to the respective partial derivatives of, I guess, each element. So I guess one example you could consider would be u of x is equal to, I don't know, like x squared plus y squared plus z squared. You can then say that nabla u is just equal to 2x to y to z, because you diff this with respect to x, and then with respect to y, and then with respect to z, and you can just write it out as a vector. Okay, so now you have the divergence definition. So this is kind of similar, except now your f is actually a vector. So it could be something like x squared, y squared, z squared. Right. If you consider the divergence of f, this would just become 2x plus 2y plus 2z. Once again, just, I guess, apply the partial derivatives to, I guess, each element of the vector and just add it up. But yeah, you guys probably would have seen this from other stuff like, I guess, 2111. So this shouldn't be too big of a shock. Okay, so now moving on to the divergence form. We say that the divergence form is just equal to minus nabla dot product with this thing here, right? And I guess the first thing you can do to convert this into the form would be to consider, like, suppose that x squared uxx plus y cubed uyy plus 2x ux plus 3y squared uy is equal to minus nabla dot product with a nabla u, right? And then now you can just kind of like consider how the derivatives kind of pair up. So if you look at these two terms here, you realize that the derivative of x squared is equal to 2x, and that the derivative of ux is equal to uxx. And then the same thing applies for these two expressions here. So what you can kind of write from here is that therefore partial derivative with respect to x of minus x squared ux plus partial derivative with respect to y of y cubed uy take the minus out is equal to is equal to partial derivative with respect to x, a plus partial derivative with respect to y, b, where this thing here is just satisfies a nabla u is equal to ab. Okay, so now you can just kind of convert this into a matrix. So you can kind of say that your A is equal to minus x squared 0, 0 minus y cubed. And then you can also say that your nabla u is equal to ux uy, right? And you also have that your A nabla u is just equal to your minus x squared ux minus y cubed uy. Right. So if you kind of just write this into one line, you have that e to the xy is equal to minus nabla dot product with the matrix minus x squared 0, 0 minus y cubed multiplied by nabla u. And that should be your whole thing in terms of your divergence form. So we're pretty much done. That's just kind of the written up solutions of the whole thing.